So, you want to learn about diffusion models. You open up a video, a blog post, a research paper if you're feeling scholarly. They tell you that diffusion models generate images by gradually removing noise from a Gaussian noise sample. Almost inevitably, this is followed by a heavy dose of mathematical notation, then pages and pages of seemingly endless algebra to prove this learning objective, which says that learning to denoise an image is equivalent to maximizing the likelihood of the data. You realize that all this amounts to is the equivalent of making sure that a deductive argument doesn't contain contradictions. Which, sure, I guess it's nice to know that it passes that bar, but so does every other generative model. So why not just go with one of them? If it takes this much effort just to prove that denoising is a valid generative model, why should we care about diffusion at all? Without answering these questions first, going through this proof just seems like a completely backwards approach to learning about these models. In this video, we'll see why denoising is just one of the pillars behind the success of these models. There's a second pillar that rarely gets treated as more than a footnote, but which has the resources to answer all these questions in a more satisfying way. This video approaches diffusion models through the lens of this second pillar, which tells us that image generation is the same thing as rolling a dice. They can be seen as instances of the same underlying physical process, and if you can do one, you can just as easily do the other. That they can be reduced to the same basic computational recipe. We'll become intimately familiar with how diffusion models rely on this insight to generate images. In the process, we'll come to realize that the second pillar isn't a foreign idea at all. It has a profound connection to the single technique that can claim an unbroken line of influence through every neural network that has ever existed. That they're just two facets of the same underlying natural phenomenon, giving us a unique insight on the very nature of solving hard problems. To understand how image generation is fundamentally the same process as rolling a dice, we need to understand the latter. What does it mean to roll a dice? Well, apart from the physical act, it's the process of sampling from a probability distribution. You can think of a probability distribution as a button that, when pushed, gives you a random observation, say heads or tails. This is what we call a sample from the distribution, such that you can't predict the value of any individual sample, but you can say meaningful things about how samples from many trials behave. For example, you would observe each face of a fair dice roughly 1/6 of the time. This long-term behavior is captured in a probability mass function, or PMF, which tells us how likely it is to observe a particular value from that distribution. Probability distributions can be discrete, like a dice roll, which means it can only take on certain values and nothing in between, or continuous, its samples can take any real valued number in a certain range, in which case it's described by a density function instead of a mass function. You're most likely familiar with probability distributions that generate samples that are one-dimensional, a single number, for example, the result of a single coin toss or dice roll. But there are also multi-dimensional distributions, which produce samples described by 2 numbers, 3 numbers, or even 1,000 numbers. They're not as scary as you might think. A 2-dimensional distribution just gives samples that are described by 2 numbers instead of 1. And the density function describes the different likelihoods of encountering each pair of numbers instead of single numbers. So, how do diffusion models relate to all of this? Well, you can think of images as samples from a very high-dimensional probability distribution. And at this point, we're ready to understand exactly what that means. If you draw a sample from this distribution, it gives you an image of something random. Could be a cat, a goldfish, a watermelon. And like any probability distribution, this means that you can assign likelihoods to individual images, and make meaningful statements about how the likelihood of different images relate to each other. And just like any other probability distribution, the full behavior is captured in a probability density function. For example, in a dice roll, we can describe the likelihood of observing a 6 as being exactly equal to the likelihood of observing a 1, and both being more likely than observing a 39, which is not likely at all. Similarly, we can describe the likelihood of some images, or certain combinations of pixel values, as higher than that of others, depending on how similar the image is to images that we would normally expect to see in the real world. Now, you might find this a bizarre and highly contrived way of framing image generation. But putting that aside for the moment and taking this proposal seriously, we now understand how images can be viewed as samples from a probability distribution. So the question now is, how do we generate samples from this distribution? Well, how do we generate samples from any distribution? You might think this is a silly question. We obviously know how to sample from probability distributions. But you might be surprised at how hard it actually is. Consider something as simple as a dice roll. How do you generate samples from the fair dice roll distribution using a computer? You might recognize that this program should sample from a uniform distribution over 6 discrete options. You might even know some libraries or tools that gives you this program out of the box, like Python's random.randint, for example. But to really appreciate how the second pillar of diffusion models uses many of the same principles of probability to tackle image generation, we're going to have to do more than just knowing how to use these libraries. What we're actually interested in is how these libraries generate these random numbers under the hood. In other words, we want to be able to implement these programs ourselves. As an exercise, think about how you would implement this right now, and let me know what you come up with in the comments. At first, you might think that as long as we know the density or mass function of the probability distribution, then we'll be able to generate samples from it. But these two things are less related than you might think. We know exactly what the functional form of the PMF of a dice roll is, but that doesn't tell us anything about how to generate samples from it. In fact, I was surprised with just how obscure the methods for producing uniform samples are. Methods like the Mersenne twister and Zoroshiro, which sound like supervillain names more than anything else. But here's some good news. If you know how to sample from one distribution, that might help you generate samples from another. For example, here's one way to generate dice rolls. First, we assume that we have access to a program that generates samples from a continuous uniform distribution, which gives values between 0 and 1, with any value in between having equal likelihood. Then we can do something like this. First, we generate a sample from that other program, and if the value that we observe is below 1/6, then we output 1. If it's between 1/6 and 2/6, then we output 2, and so on. This is a sample from the dice roll distribution. It gives each face of the dice roughly 1/6 of the time. Now, you might not be too impressed with this, given how similar these two distributions are. After all, they're both uniform distributions. But there's another distribution that, if you know how to sample from it, can generate samples from almost any other distribution. And if it works for any distribution, we can use it to generate samples from a probability distribution of images, which might give us a hint as to how the second pillar can generate images as easy as we might generate dice rolls. This distribution is none other than the normal distribution. To see how this is possible, let's take a step back from dice rolls, which we saw was reducible to drawing samples from a continuous uniform distribution, and take a look at a slightly more complicated distribution with a density function like this. We'll call this probability distribution P2 peaks. I'm also going to make a further relaxation that we don't know the exact functional form of this distribution, just that it looks something like this. Now, I claim that we can generate samples from P2 peaks from just knowing how to generate samples from the normal distribution. Okay, we actually need one more thing here. We need access to a particular function which we'll call f2 peaks. It takes in a location on the sample space and returns the direction that most quickly increases the likelihood that a sample comes from P2 peaks. So in this case, for any location in the x-axis, xi, f2 peaks of xi would tell me if I should move to the left or to the right in order to most quickly increase the value of P2 peaks. So if we have this function, f2 peaks, along with an ability to draw samples from the normal distribution, it turns out that there's a very simple procedure that generates samples from this distribution, called Langevin sampling, named after French physicist Paul Langevin. First, you start at an arbitrary location in the sample space. Let's call this value x0. Then you're going to move in the direction of f2 peaks at x0, the output of the function f2 peaks, evaluated at that location x0. This takes you from x0 to somewhere in the sample space that has a higher probability density or a higher likelihood than x0. Let's call this new location x0 prime. Then you generate a new sample from the normal distribution, multiply it with some small number, and add it to x0 prime, bringing you to a new location which we'll call x1. This process of bringing you from x0 to x1 is one Langevin update. It updates the location of your initial sample x0 to some new nearby location x1. Now, here's the cool part. The more times you repeat this Langevin update, each time starting at the location that you got from your previous update, the more your sample resembles a sample from P2 peaks. So I can generate samples in the following way. First, I'll generate a random sample from a normal distribution and treat that as my x0, and perform 1000 steps of Langevin updates. The result that I get, x1000, is a sample from P2 peaks. One quick way to verify this is to draw many samples using this process, each time performing 1000 iterations of Langevin updates, and see that the histogram of samples that I get roughly matches the shape of the PDF. Now, you might notice that it slightly oversamples on this smaller peak at the right, and that happens because of the approximate nature of Langevin sampling. Samples from this process only converge to samples from the true distribution in the limit of an infinite number of Langevin updates. But since we can't wait an infinite amount of time just to get a single sample, the samples you see here are obtained after only 1000 updates each. In this case, 1000 updates turns out to be just enough to capture the essence of the distribution, while still showing some noticeable differences. Now, you might be wondering, why does this work at all? We're not going to formally prove it in this video, maybe in a future one, but intuitively, we know that for P2 peaks, most samples would cluster around one of the two peaks. F2 peaks brings you closer to one of the two peaks, depending on where you are right now. So you can immediately see how knowing F2 peaks helps us generate samples from P2 peaks. But it's not enough. If our Langevin updates only consisted of the F2 peaks term, without the additional samples from the normal distribution, you would only ever generate samples that took the exact value of either peak. But these are obviously not samples from P2 peaks. We need to add some randomness to the determinism of F2 peaks. And that's why we add Gaussian noise, samples from a normal distribution, to add some realistic variation. One small note about this F term here. I described it as the direction that most quickly increases the likelihood that a sample comes from the distribution we're interested in. To be more precise, f is the gradient of the log of the probability density function of the distribution that we're interested in. We're familiar with this term, the PDF, and the gradient of the PDF is simply its first derivative. Even without the logarithm, the derivative of the PDF is quite a natural way to formalize the idea of the direction that most quickly increases the likelihood. So the question is, why do we need this logarithm? Well, imagine we're using the raw gradient without the logarithm. If you started with an x0 that's very far away from the peaks of the distribution, you can see that the gradient is really small because the slope of the curve at that location is just very small. So it would take a really large number of Langevin updates to reach one of the peaks of the distribution where all the likely samples actually live. But the slope of the log of the curve is actually pretty large. So adding a logarithm serves to increase the magnitude of the gradient in those regions, so you can reach the peaks of the distribution quickly. You can see this directly by applying the log derivative rule. The derivative of the log of a function is equal to the derivative of the function divided by the function value itself. So the first thing to notice is that this f term actually contains the derivative of the PDF without the logarithm, but with an important modification. It gets divided by the value of the PDF, the likelihood, at that location. The division by the PDF naturally acts as a scaling factor that achieves the effect that we wanted. In places where the PDF, or likelihood, is low, the divisor is going to be small, and so it increases the magnitude of the gradient. So now that we have a good grasp of Langevin sampling, let's use it to write our own algorithm for dice rolls. This will serve two purposes. It'll help us see what it takes to use Langevin sampling on a real problem, and warm us up on how we can use something like this to generate images. We'll approach the problem like this. First, we'll use Langevin sampling to generate samples from the continuous uniform distribution. Then, we'll simply apply a threshold on the value of the sample to decide which face of the dice is sampled. Remember that we need two components for Langevin sampling: a way to draw samples from a normal distribution, and the function f for the continuous uniform distribution, f uniform. For the first component, we'll just use an off-the-shelf sampler, like NumPy's random.normal. We'll assume that we have this subproblem solved. For f uniform, we need to think about a function that takes in a location in the sample space of the uniform distribution, a number between 0 and 1, and returns the gradient of the log likelihood of the sample under the uniform distribution. Since a uniform distribution's density function has the same value everywhere, f uniform really can't bring you to a location where the density is greater than wherever you started from. So f uniform is simply 0 everywhere in the sample space. However, we do need to take care of the boundaries of the sample space. Since this is a uniform distribution, we must never generate samples that are outside of the sample space, like -0.2 or 1.5. I'll handle this using some potential walls. F uniform evaluated at a location smaller than 0 should point to the right, and F uniform evaluated at a location greater than 1 should point to the left. I'll admit that I had some trouble getting this to work cleanly. The main issue was figuring out how strong F uniform should be in these boundary cases. It has to be strong enough to push the sample back inside the range of 0 and 1, but not too strong that it simply pushes it back out the other boundary. So the full program would go like this. I want to point out here that in no way was it obvious to me that this procedure, Langevin sampling, would lead to samples from a uniform distribution, especially since the F uniform term is just 0 everywhere, except in the places near the boundary. So this procedure amounts to simply adding samples from a normal distribution repeatedly. How could that process lead to a uniform distribution? But when you draw 10,000 samples using this program, the samples are unmistakably uniform. As a reference, here's 10,000 samples drawn using a true uniform distribution. if I didn't tell you which histogram was generated by which method, you probably wouldn't be able to tell which was which. So these are the samples drawn from the continuous uniform distribution, which was step 1 in our strategy for generating dice rolls. To derive the actual dice rolls, we'll apply step 2 to every sample from step 1, giving us this histogram. And sure enough, we get outcomes of a fair dice roll, with each face of the dice occurring roughly 1/6 of the time. Of course, this is a very inefficient way to generate samples from the uniform distribution. Off-the-shelf solutions like NumPy's random.uniform use specialized algorithms that are much faster for the uniform distribution. But what I find significant is that we derived this algorithm ourselves from first principles, and that the same procedure works for this distribution, the distribution with the 2 peaks that we used earlier, and as we'll soon see, a distribution as complex as the probability distribution of images. Think of an image that has a size of 1000 pixels by 1000 pixels. That's a million numbers, each of which can take values between 0 and 255. That's the range of values that a pixel can take. We're going to pretend that there's some probability distribution that generates these images as samples, much like how a dice roll generates random samples that are the possible faces of the dice. This probability distribution of images generates random samples that are images. Like any other probability distribution, this distribution, let's call it p images, is governed by an underlying probability density function that describes the likelihood of getting different images. When images are viewed in this way, as samples from an albeit unknown probability distribution, we should be able to generate samples, new images, by performing Langevin sampling. As before, we'll need the f function of the image distribution. Recall that this is a function that takes in an arbitrary location in the sample space, in this case the space of all possible images, and returns the gradient of the log likelihood of the sample under the distribution. Of course, it's not going to be as simple as our previous examples, as they were all one-dimensional problems. Samples from p2 peaks and p uniform can be described by a single number, so the sample space can be depicted by a single x-axis, freeing up the y-axis to depict the PDF of the distribution, telling us which points in the sample space are more likely than others. As we discussed before, the f term in these cases is a direction in the one-dimensional sample space, either left or right, depending on where you are, with the magnitude of the f term manifesting in the length of the arrow. For two-dimensional distributions, those that produce samples that are described by 2 numbers instead of 1, we need 2 axes to depict the sample space. Any location in this 2-dimensional plane is a possible sample, and now we need a 3rd axis to depict the PDF, which now describes how likely it is to observe each pair of numbers under this distribution. But remember that for the purposes of Langevin sampling, what really matters to us is the f term. In this 2-dimensional setting, f is a direction in the 2-dimensional sample space, pointing where you should step to most quickly increase the value of the PDF, with the length indicating the magnitude of f. Of course, this direction and magnitude depends on where you are in the sample space. That's why f is a function of your location in sample space, just like how it works in the one-dimensional case. And just as we discussed earlier, the nature of the logarithm in the f term makes it so that arrows further from the peaks have larger magnitudes, and arrows closer to the peaks have smaller ones. To describe a 3-dimensional distribution, we need 3 axes to depict the sample space, and we need to get creative about depicting the PDF itself, since we've taken up all 3 of our spatial dimensions for the sample space. So for this particular 3-dimensional distribution, I'm plotting the samples I get from the distribution, as well as coloring more likely samples red and less likely ones blue. to paint a picture of what can only be fully visualized in 4-dimensional space. You should be getting the hang of what f should look like by now. They're simply directions in 3D space that most quickly increases the value of the PDF, again with the length indicating the magnitude, and with arrows further from the peaks having larger magnitudes compared to arrows closer to the peaks. Once you get to 4 or 5 or higher dimensions, even the samples themselves can't be depicted as locations in 3D space. 1 million dimensional images live in a 1 million dimensional space, and the F term is a direction in 1 million dimensional space. We can't really visualize this, but I find the 2D or 3D setting gives you a good idea of what this means, if we just pretend that there's 1 million axes instead of 3. Not being able to visualize the distribution is the least of our concerns though. To use Langevin sampling for image generation, the bigger obstacle is the fact that we don't know the exact analytical form of the PDF of the probability distribution of images. And as a result, we can't calculate the F term for images by taking derivatives from the PDF. For our dice roll exercise, we knew the exact analytical form of the PDF of the uniform distribution, so we could directly take the log, then the derivative, which simply evaluates to 0 everywhere, barring the boundary cases that we talked about. But for images, what is this PDF? It would have to be a function that takes in the 1 million pixel values of an image, then computes the probability that that image would be sampled from the distribution, as a function of those 1 million pixel values. We have no idea what this function could be, so we can't just get the F term by taking the derivative of this function that we don't know. We do, however, have a rich collection of images of pretty much anything from the internet. You can think of these as existing samples from the distribution that we're interested in, p-images. This is where the first pillar, deep learning, comes in. Instead of needing full knowledge about the F term for the image distribution, there just so happens to be a class of neural networks that can estimate the F function directly from samples, thus circumventing the need for an analytical form for the PDF. These neural networks are none other than the star of our show, diffusion models. In part 1, I framed diffusion models as a certain type of navigator of image space. Starting from any point in the space of all possible images, diffusion models learn the direction that points to the closest cluster of good images in the million-dimensional sea of nothingness that is image space. If you have this navigator, you can generate images by starting at a random location in image space, then repeatedly taking small steps towards a good image by following the directions that the diffusion model gives you. Every time you take a step, mathematically, this means adding the diffusion model's prediction to your current location, and geometrically, this means taking a step in image space from your current location to some new location that's closer to a cluster of good images than where you were before. Repeating this process generates your image, and puts this entire process inside a loop. At this point, we're ready to reveal the real meaning of the direction that the diffusion model predicts. It's secretly the gradient of the log PDF of the probability distribution of images, which is exactly the F term that Langevin sampling needs. And this is actually quite a natural interpretation just from the structure of image space that we explored in part 1. If you imagine image space as the sample space of some probability distribution, and the individual images as samples from that distribution, then these clusters where good images live are regions in image space that are the densest. They have a high number of samples per unit area. In other words, where the value of the probability density function is high. So if we accept that diffusion models point to clusters of good images, that means that they point from locations in the sample space where the density is low to locations where the density is high. And this is just what a gradient is. They're directions that will lead to the greatest increase in the value of a function. In this case, the probability density function of a distribution. Notice that this image generation process, which we developed in part 1, is already really close to Langevin sampling. All we need to do to make it identical is adding the noise term in addition to the F term at every step. And from this video, we're ready to understand why we need the noise term. It ensures that the output of this process results in a proper sample from the distribution, and not just always returning the peaks of the distribution. This means that the actual path that the image takes is more like this squiggly, noisy path instead of the clean one we saw in part 1. So we finally have the full picture of the different roles that the two pillars play. The second pillar, Langevin sampling, frames image generation as sampling from a probability distribution, utilizing the insight that you can generate samples from any distribution if you know the F term or the gradients of that distribution. If you know the gradients, you can start at a random location in the space of all possible images and just follow the gradients to a good image, interleaving your gradient steps with random noise to ensure you get a proper sample from the distribution. But the problem is that we don't know what the F term is for the image distribution, and the first pillar, deep learning, solves this by learning to approximate the F term from data. This is why an explanation of diffusion models that doesn't contextualize the first pillar in light of the second will always be incomplete, which is why it's unfortunate that most resources seem to only care about the deep learning aspect. I'll touch on why I think this is happening in a future video, but it's not entirely surprising. Even the name diffusion model implies that a model or a neural network is the focal point of the method, entirely overlooking the fact that there's a non-neural network component that is arguably even more important in making the system work. Diffusion model is such a bad name that it's unclear if it refers to the whole system that generates images, or just the neural network component, which is the component that's actually the model, which by itself cannot generate images. This brings us to a common missing piece that I see in explanations of diffusion models. People usually present a noising-denoising perspective. There's a forward diffusion process of adding noise gradually to an image, which transforms it to pure noise. Then we have a neural network, the diffusion model, that learns to reverse that process, allowing us to generate images from noise. Well, if that was the full story, then why do we need to add more noise throughout the entire reverse process? This seems to contradict the denoising perspective. If image generation is purely a denoising process, wouldn't adding more noise make the result worse? So there has to be more going on here. What exactly is the noise term adding to the system that the neural network can't do itself? Well, one quick way to probe at this question is to just remove the part of the sampling code that adds the Gaussian noise, making our Langevin updates purely consisting of the F term. Let's say beginning at iteration 500 out of the 1000 that we're doing. In this one, I'm asking the model to generate a red panda. And you can see that it starts off by generating the outlines of what is unmistakably a red panda. This is the first half of the process, where we're still adding in the noise term. Then at some point, it sort of loses interest in further refining the details of the panda, and makes the image blurrier and blurrier. This is the second half of the process, where we removed the noise term and purely follow the diffusion model's directions. So what might be going on here? Well, remember that removing the noise term for P2 peaks results in samples that took the exact value of either peak, which are clearly not samples from P2 peaks. If they were, we'd expect to see more variability in the samples. We're seeing a related phenomenon for images here, but the situation's a little more complicated. To help us see why, let's pretend, as in part 1, that this two-dimensional plane represents the space of all possible images, with plausible images clustering around small pockets in the space, with this landscape with 4 hills representing the probability density function of the distribution. I had mentioned in part 1 that this description is in many ways just a caricature of the actual probability landscape of images, and one important way that this was oversimplified is that the actual landscape of a highly complex probability distribution, like that of images, is likely to be a lot bumpier and messier than I initially portrayed, with small hills everywhere that might have a high likelihood compared to the valleys that surround it, but low likelihood compared to the summit. Do you see the problem? Well, if you start at a random location and just follow the gradients of this landscape, you'll most likely end up in one of these small hills, what we call local optima, so called because once you're in one, moving in any direction will only lead to an immediate decrease in the likelihood. So the gradients will always point back to that small hill, even though there are more advantageous global optima, locations in the space where the likelihood is much higher. So this blurry prototype of a red panda might very well be less likely or less probable than an image with more details. But since diffusion models are short-sighted because they approximate the gradients of the probability distribution, it might have gotten stuck inside one of these local optima in the highly complex terrain of the distribution. And without adding further noise, we sort of stopped it from stumbling into regions where the likelihood is higher. So what we observed from this experiment might be a combination of both these factors, and the noise can be seen as playing multiple important roles. It ensures that there's enough diversity in our samples to reflect the diversity of the probability distribution we're working with. This result comes from the theory of Langevin sampling. And to pull the samples out of suboptimal local optima, using random directions in the sample space, as sort of a trick to combat the short-sightedness of the gradient. So these are broadly theoretical reasons for why we need the noise term. But at this point, I want to provide one more intuitive perspective on this relationship between the two pillars, one that might have something to say about why diffusion models are more successful than other popular architectures, like generative adversarial networks or variational autoencoders, although all three have their strengths and seem to have carved niches where they're favored over the others. If we take a look at the image that was produced at the midpoint of our experiment, at the exact moment that we switched from adding noise to not adding noise, it almost looks like it's a better red panda image than the one that we got at the end, after we completed the second half of the algorithm by purely following the diffusion model and adding no noise at all. It seems like the diffusion model is actually destroying the details of the image that was already there. This is because high-resolution detail, pixels that change in color very rapidly in a small patch of the image, is the responsibility of the noise term to add. The diffusion model can only selectively edit the noise at strategic locations, making some of the pixels to be the same value instead of different values in certain meaningful ways. This tells you that noise is sort of the raw material of an image that the diffusion model uses to sculpt the image. If there's not enough noise injected into the image, then the diffusion model simply runs out of material out of which it can create a good image. I find it useful to think of the diffusion model and the noise term as a two-person team of artists, one methodical artist and the other a creative one. The noise term is the creative half, painting random patterns on the canvas. Then the diffusion model steps in and kind of tones down the craziness of the noise term, telling it, hey, don't be so chaotic. See, if I just remove this smudge here, clean up that jumble of colors over there, we get something like a line or an edge, which are the building blocks of a good image. Put many lines together in certain arrangements, and we get shapes, textures, and before you know it, ears, snouts, and other friend-shaped things. At first glance, the noise term, or the creative half, looks like it's trying to destroy the painting. But ironically, this is the only way that the two people can get anything done. See, the diffusion model is trained to remove noise from images that we artificially added noise to, removing unnecessary high-resolution details in the painting, not to add details to a painting that lacks them. So the diffusion model isn't creative enough to know that it ever needs to add some details. And the noise term isn't smart enough to know what kinds of smudges or details depict a meaningful pattern. It's easy to think that the diffusion model is the one doing the heavy lifting, since it's the one that takes a lot of resources to train, and which has to understand the structure of the probability distribution, while the noise term doesn't have to do any of that, and we get it for free. But I find this perspective helps me viscerally realize that the noise term is just as important as the diffusion model in obtaining high quality or high probability images. From a mathematical perspective, the noise term is crucial for pulling us out of local optima and finding regions in the probability landscape that have a higher likelihood. From an intuitive perspective, the noise term takes on the responsibility of being creative, allowing the diffusion model to focus on the logical capabilities. And working together, they become more effective at the task that they're trying to accomplish, generating high-quality images. This seems like an unusual way to create art for humans, but from a machine learning perspective, this is a great design decision. The problem with using machine learning to solve a task that requires both creative and methodical capabilities is that these are very much conflicting optimization objectives. The more you train a neural network to be increasingly logical, to the exclusion of everything else, the less capacity it has to be creative. Generative adversarial networks, for example, would have to learn to internally balance the creative and methodical capabilities in a single neural network, deciding which exact layers should deploy which capability and to what extent. And sure enough, GANs are notorious for their training instability, and even if you do manage to train one, they are prone to a phenomenon called mode collapse, in which they seem to sacrifice creativity in favor of generating a homogeneous type of high-quality image over and over again. Diffusion models, on the other hand, offload the creative capability to pure random noise, which you can think of as a perfectly creative and perfectly non-logical agent. This not only makes them extremely easy to train, the model now needs to only focus on optimizing the logical capability, unencumbered by the creative constraints, but also leads to more diverse images, due to not suffering from mode collapse like GANs do. I don't know how much the authors were thinking about this when they first proposed diffusion models, but in hindsight, this separation of responsibilities makes perfect sense. And from the rest of this video, we know that there's a theoretical motivation for this approach to image generation, Langevin sampling, which connects image generation to tossing a coin, rolling a dice, and many other probabilistic processes, as different instances of the same fundamental process, that of sampling from a probability distribution. Okay, I know that was a lot to take in, so let's make sure we grasp what we've just achieved. We used the exact same procedure, Langevin sampling, to generate both dice rolls and new images. In fact, Langevin sampling is a general procedure that can produce samples from any probability distribution. This isn't just theoretical. DeepMind's AlphaFold 3 uses diffusion models to predict the structure of proteins better than we've ever been able to do. The best robotic foundation models use diffusion to generate robotic control actions that can do pretty amazing things. Diffusion is a good contender for being the best at music generation, video generation, and even language modeling. This might be the most surprising fact that I've learned in AI for a long time, that to obtain a sample from any probability distribution, no matter how simple or complex the distribution is, or if the samples have one dimension or a million dimensions, you only need the gradients of that distribution. You don't need to know the density function itself, and not even the second or third order derivatives, no. You don't need to know anything else about this distribution other than the gradients. And to obtain the correct kind of variability, doesn't matter if it's the really simple kind involved in a dice roll, or if it's all the intricate ways that pixels in an image can vary to portray an endless collection of concepts. The standard Gaussian distribution is always the answer. And I find that extremely surprising. One of the strange things about our universe that feels like it just shouldn't be true. But the fact that diffusion models are so useful in so many seemingly unrelated problems tells us that it is. Some of you might recognize another area where an iterative gradient-based optimization method seems to be unreasonably effective: gradient descent, namely the very mechanism by which we train deep networks. In gradient descent, we repeatedly update the parameters of a neural network to stochastically maximize its performance, or minimize its loss, on some task defined by some dataset. In image generation, we repeatedly update the image's pixels to stochastically maximize the likelihood that it came from the probability distribution of images. You can also think of the likelihood as the quality of the image, so we're stochastically maximizing the image quality. In gradient descent, we can analytically compute the gradient of the loss on a small batch of samples from the dataset with respect to the network's current parameters, using the randomness induced by the mini-batch to take us out of local optima and find higher performing parameters. In image generation, the gradient of the likelihood with respect to the current pixel values is approximated using a diffusion model, and we explicitly inject randomness by adding Gaussian noise to take us out of local optima and find higher likelihood regions. Of course, diffusion models themselves are trained using gradient descent, making them deep networks that use iterative gradient-based optimization in both train time, gradient descent, and test time, Langevin sampling. What's remarkable here is that we use gradient descent for everything in deep learning. Doesn't matter if we're classifying images into cats versus dogs, detecting humans on the road, or if it's literally ChatGPT. Or indeed, if it's predicting the gradients of the probability distribution of images. They're all trained using the exact same algorithm, gradient descent. In fact, in a field where ideas are plentiful but only a few really stick, gradient descent might be the only technique that no one has been able to unseat from its throne since it was proposed. I found this to be an interesting parallel to how Langevin sampling, the principle that diffusion models hinge on, works for any probability distribution, from dice rolls to controlling robots, all the way to image generation. This seems to point to some kind of unreasonable effectiveness of stochastic gradient-based optimization. To solve hard optimization problems really well, it seems that you only need to know where to move to improve your situation a little bit from where you currently are. In other words, the gradients of the objective or goal that you're trying to optimize, whether that's the loss of a neural network on some training dataset, or if it's the likelihood of an image, sprinkled in with some random noise, or luck, to take you out of local optima, break you out of a rut when you get stuck. And you can keep repeating this process of making small steps following a noisy gradient for as long as you need, depending on the difficulty of the problem. In the case of gradient descent, until the training loss on your dataset or task is at a minimum, or in the case of Langevin sampling, until the image you get has a high enough likelihood. From this perspective, the second pillar, Langevin sampling, is not a foreign idea at all. Instead, it's just a different manifestation of the same underlying principle, that gradient descent, combined with an ability to use more compute according to the difficulty of the task, is an extremely powerful and versatile framework for solving hard problems. And if they work so well in train time, then we should use them at test time too. There's been some hints of this insight throughout the years. ResNets, for example, popularized the idea of making small adjustments, residual connections, but doing this a lot of times, let's say for 1,000 layers. But I think we'll come to view diffusion models as what finally made this idea mainstream, by quite literally having a stochastic gradient descent algorithm, Langevin sampling, as its inference procedure. Even after covering so much ground in this video and the previous one, it's amazing that there's still so much more to say about diffusion models. For one thing, there's a small problem with using Langevin sampling, as described in this video, in large swaths of image space. Some of you might have picked up on it. Remember how I said that most of image space is empty in the first part of the series? So if you zoom into any particular empty region of image space, there are absolutely no samples anywhere in that local patch. This means that the gradient in those regions is exactly 0. There's nowhere you can go within this local patch to increase the likelihood of the sample under P images. So if you started off your image in any of these empty local patches, your Langevin updates would consist purely of the Gaussian noise term, and it'll be practically impossible to stumble near one of the small clusters of image space where good images live, just using random noise. This tells us that Langevin sampling isn't a perfect solution for absolutely all probability distributions. Solving this problem is one of the engineering innovations of diffusion models. They effectively add some fake samples in these empty areas, making the gradient technically non-zero everywhere in image space, while still pointing to where the true samples are. Another missing piece here is seeing why diffusion models output exactly the F-term required for Langevin sampling. In the first part of this series, we described the training process of diffusion models as a very simple denoising task. First, you add random noise to images from your training set, then ask the model to predict the noise that was added. But from this video, we know that Langevin sampling needs something very specific: the gradient of the log PDF of the distribution that we're interested in. And it's really not obvious that predicting the noise added to an image is the same thing. So the original author of this technique, which is called score matching, had to prove this equivalence. In part 3 of the series, we'll examine the challenges the authors faced in trying to formulate a machine learning task for this gradient term that's actually achievable with a reasonable amount of compute. And we'll go through all the mathematical tricks that they pulled to do this, culminating in proving this equivalence ourselves. The last piece of the puzzle here is trying to understand why the Langevin update is the way it is. Why is it that this gradient descent looking algorithm, where you keep making small steps according to the noisy gradients of the distribution, able to produce a sample from any probability distribution that you can think of? This will take us far afield from machine learning and into statistical physics, so is likewise a topic for a future video. But let me know in the comments if you were as blown away by this as I was. In the meantime, sit tight for part 3. I'll see you there.